In this video, we are going to be talking about the concept of population ecology, and we'll be looking basically into the overview of population growth model. Although life history describes the way many characteristics of population change over time in general way, population ecologists now make use of variety of methods to models population dynamics mathematically. And this more precise model can be used accurately to describe changes occurring in a population and better predict future changes. And certain long accepted models are now being modified or even abandoned due to their lack of predictive ability, and scholars strive to create effective models. Now, the first thing we have to understand is what is population itself. You see, population is the assemblage of individuals of the same species, or we can say that population is the total number of individuals inhabiting a specific area at a given time. And when we talk about individuals, we are talking about individuals of the same species. And when we said species, we all understand that species is the unit of classification. That is group of animals that are capable of interbreeding with each other under natural condition. You understand? Under natural condition, they can interbreed with each other, and under natural condition, they cannot interbreed with species of another level, right? Remember that in the classification of life, we have kingdom, we have phylum, we have class, we have order, we have family, we have genus, uh, we have species, right? Now, species is now the lowest level, you understand? In species, we can have the genus to be Homo, for example, in human, and the species to be sapien. So we are Homo sapiens, you understand? Now, under natural conditions, humans can live together, they can inhabit together, you understand? Now, when we are calculating the population, we are saying how many humans, it is humans. So we are saying organism of the same species is inhabiting this specific area at a specific time, you understand? So the total number of individuals or species within a particular space at a given time is what we refer to as population or population size, you understand? Now, in ecology, just like we have species, assemblage of species now give what we refer to as what we refer to as population. So if a species if species comes together, they form population, and if population comes together, they form what? They form community. Community. You understand? So basically, you see, population ecology usually deal with it from species level to what? To community level. Because the assemblage of community is now going to form the biosphere, and the assemblage of biosphere is going to form the ecosystem itself at large, you understand? But we are mostly concerned with the concept of population and community, you understand? Now, let's now talk about what we are focusing on today, which is the overview of the models of population growth. Now, when we say population growth, we are talking about the change in the number of individuals in a particular area over time. We all know that population is total number of individuals, right? So we are now saying that how do they change in number over time? That is basically what population growth is. How are they changing over time? Is it decreasing? Is their number decreasing? Is their number increasing? You understand? So this population growth is now influenced by it. By what? By birth rates. Either they are increasing with number as they are giving birth rates, which causes decrease in population, immigration, which causes increase in population, and immigration is the movement of group of animals from one place to another. You understand? Moving in, that is immigration. And the fourth one is emigration. You understand? Emigration is moving out. You understand? Moving out. And environmental factors. Some environmental factors can also influence how a population change with respect to time. So we can say that population is a function of time. You understand? If we say that population is a function of time, we are not wrong. You understand? Because it is the change in the words population growth is a function of time. So we can say that population growth is the change in the number of individual in a particular area over a time. And when we say something is a function of time, therefore we are going to take it into the concept of calculus, which we are going to be using very, very soon. So population size is dynamic. When we say that it is dynamic, it means it is not stable. It changes over time. You understand? Now, understanding these changes now allow ecologists to profound models, and these models is used to predict population growth, and this prediction in population growth will now let us to know how we can manage this population over time. You understand? So we use a model in prediction population growth, either it is increasing or decreasing, and we are going to use this prediction to know how we are going to manage this population over time. You understand? Now we now have different types of population growth model. We have the first one to be the exponential growth, which is the exponential growth model, and the second one to be the logistic growth model. Now, you see, neither of these growth model describes natural population, but they provide an essential theoretical framework, because you need to understand the simple ones before you understand the complex ones. That is basically the rule of everything. You understand? So we need to understand this growth model before we can understand other growth model. We have a lot of growth model. We have the standard age growth model. We have the Leslie's matrix. We have a lot of them like that. You understand? But the ones that you have to understand first is the exponential growth model and the logistic growth model. Now, in the logistic growth model, Charles Darwin, in his theory of natural selection, was greatly influenced by an English clergyman that we refer to as Thomas Malthus. You understand? Now, Malthus, he published his own book in the year 1798, stating that population with unlimited natural resources grows very rapidly. Like when a population has unlimited resources, they have enough food, they have good climate, they have good weather, there is no death, they grow, they grow very rapidly, they continue growing. You understand? Now, this rapid growing is now what we refer to as what we refer to as exponential growth. So exponential growth is what we are trying to say that, according to Thomas Malthus, it says that when a population has infinite amount of electricity, infinite amount of natural resources rather, unlimited number of resources, they grow very rapidly, like they continue growing. You understand? And that is what we refer to as what we refer to as the exponential growth. Now, if want to explain the exponential growth, is best explained like it is best explained as it is seen in bacteria. You see, bacteria undergo what we refer to as prokaryotic fission. Prokaryotic fission in a way that we are going to have a bacterial cell like this. You understand? Inside the bacterial cell, there will be division of the nucleus into two. I'm just trying to represent it. You understand? So let me just put one ciliary. Now I'm just trying to represent it. You understand? Now, these two, as it's separate in nucleus, there is going to be a binary fission or prokaryotic fission. So it's now going to give a what? It's going to give two daughter cells. So one amoeba and one bacteria is going to give two bacteria within an hour. You understand? Within an hour, one bacteria is going to give two bacteria. Then two bacteria will give four bacteria. Four will give 16. 16 will give, you understand? That is how it continues. So what they are trying to say is that if a bacteria is placed, you understand, if a bacteria is placed in a petri dish in an environment, it is cultured in an environment and it's supplied with unlimited nutrients, unlimited nutrients, they continue to grow. You understand? So if we start with 1,000 bacteria, 1,000 bacteria we divide, we give 2,000 bacteria. 2,000 bacteria we divide to give 4,000 bacteria. 4,000 bacteria we divide to give 8,000 bacteria. Can you see? And after 24 generations, you are going to be seeing 16 billion individuals. You understand? So it is an exponential growth because we supply them with unlimited nutrients. They have nutrients that they need to grow. What we prefer, what to prevent them from growing? Nothing. You understand? So they grow exponentially. You understand? Now, if you now want to draw that particular growth curve, If we want to draw either particular growth curve, we are going to draw it like this. We are going to say that this is the population growth, this is the population growth, and this is time. You understand? This is the population growth, and this is time. So we see that it starts like this, then it goes upward rapidly, like it continue going like that. She understand what I'm trying to say? It continue going like that, like nothing will stop it. It will continue growing. You understand? It will increase exponentially. Now you see, we now have two type of phase in this particular graph that we have here. We have the lag phase, you understand, and we have the log phase. So this is the lag phase, and this is the log phase. You understand? Lag phase and log phase. You see, lag phase and log phase, they are the two sequential stage of a microbial growth. As a microbiology student in microbiology, they are going to teach you lag phase and log phase. Lag phase, both lag and log, they are what? They are the first two sequential stages of microbial growth. You understand? That is in a culture, like that has been cultured. Now you see in lag phases, during lag phases, you see that it is going like it goes straight. During lag phases, there is no cell division, which means the population remain constant. Are you getting me now? And it can range from an hour to several days. Now, in log phases, the cells have successfully adapted and begin to divide rapidly. 1 becomes 2, 2 becomes 4, 4 becomes 8, 8 becomes 16, 16 becomes 32, 32 becomes 64, and they continue to go like that. So during lag phase, there is no cell division. Why? Because the population is just being introduced in that particular environment. Assuming that you are camped in an environment that you did not know before, you and one other person, you understand, what is the first thing you are going to do? You are not given any food, you are not given anything, or you are even provided with food. Let me say you are provided with unlimited things. What's the first thing you are going to do? Let me try as much as possible to arrange my things, right? I'm arranging my things and arrange my things. Okay, let us cook food, let us do this, let us do that. It was not after you are comfortable where you are, that is when you can start reproducing. That is exactly what is happening in lag phase. Is when you are trying to accommodate, when you are trying to adapt to that particular environment. And in log phase is when you try to what? When you try to replicate, when you try to reproduce. You understand? So it is now saying that during this reproduction, it increases exponentially. It continues like that. It does not stop. Do you understand? That is basically what they are trying to explain here. Can you see the lag phase and the log phase? So with time, it increases exponentially. Are you getting me now? But a bacteria example is not representative of the real world where resources are limited. Because look at this Nigeria now, look at the whole world. The resources are limited. You understand? So furthermore, some bacteria will die during the experiment. Thus, some will not reproduce. That is, there is going to be lowering in the growth rate. So when calculating the growth rate, two things have to be involved. That is the death rate and the birth rate. These two factors are going to be considered in real world, like in real world time, where where there is limited resources. Death rate is going to be considered, birth rate is going to be considered. You understand? Now, in considering this death rate and birth rate, we will now arrive at a particular formula. You understand? And that formula is what? That formula is the n, which is change in the n means change in population over time equals to what? Equals to birth rate minus death rate. You understand? Birth rate minus death rate. That is the formula. You understand? Now, this is the formula that we have first. Now, the birth rate is usually expressed in per capita, and the birth rate is usually expressed in per capita as well. So we now try as much as possible as an ecologist. We know that this thing is going to change at a particular instant time. You understand? And we are differentiating with respect to t. Are you getting me now? We are differentiating, we are changing number of population with respect to time, which means we can say that therefore my dn upon dt will be equals to b minus d over what? Over multiplied by n. You understand? Now we have this. We have this now. You see, b minus d is now rate of increase, like r. Sorry, rate of increase, small letter r, small letter r. B minus d is small letter r. And this small letter r is what we refer to as intrinsic rate of increase. Intrinsic rate of increase. That is the small letter r that we have there. Which means anywhere we see b minus d, we can represent with r, which means our dn, differentiation of n with respect to t, equals to what? It equals to rn. We have this. This is the first formula for the exponential growth model. You understand? This is the first formula for the exponential growth model. Now, we have this already. We are good with this, right? Now, in this particular material, we now have something like this is the n upon dt equals to rn. Now, how do we now come about this nt equals to n naught exponential rt? How do we come about that? Now, you know that this is a differential equation. And when we are talking about differential equation, it is not suitable for exponential growth. Whenever you want to describe an exponential growth, you are going to use an integral formula, an integral form. You understand? Now, in using an integral form, we are going to integrate the both sides. What you're just going to do is that what we have dn upon dt equals to rn, right? Therefore, equals to rn. Therefore, we can cross multiply. Therefore, our dn equals to rn dt. The next thing we can do is what? We are going to integrate the both side. And integrating the both side, nt will be our upper limit, n naught will be our lower limit, t will be our upper limit, 0 will be our lower limit. You understand? That is integration at time t and at time 0. You understand? Now, after integrating, we are going to be having what? We are going to be having nt, right? We're going to be having nt over, or we're going to be having ln nt over n naught equals to what? Equals to rt. That is what we are going to be having. That is if you integrate this particular formula, you are going to be having ln of nt over n naught exponent rt. Now, to cancel this ln, we are going to use the exponents in the both side. You understand? So exponential is going to cancel out ln. Therefore, we are going to be having what? We are going to be having nt over n naught equals to exponential rt. So we can cross multiply now. Therefore, our nt equals to n naught exponential rt. And that is where we get this particular formula from. That is nt equals to n naught exponential rt, where our n is the population size, our r is the intrinsic growth of rates, which is b minus d, our t is time, and our e is Euler's number that we refer to as exponential. You understand? Now, our nt is population at time t, our n naught is initial population. You understand? Now, if the r, which is the intrinsic growth of rate, is greater than 0, the population increases. If it is equals to 0, there is no population growth. And if it is less than 0, the population decreases. You understand? Now, the limitation is that there is no environment that you will live there will be unlimited resources. It's not possible. The resources will be limited. So, and it is very rare in nature for you to see where there is unlimited resources or where an exponential growth will occur. You understand? Now, let us now do an example. They say you are studying the population of agricultural pests that has been introduced to a local farm because there is no known predators of this pest. Its population is growing quickly and without any trace of slowing down. You worry its population will declimate the crop, and you want to know what the population will be in 5 years. Your sampling of the pest population gives you 234 individuals. You understand? Which means your initial equals to 234 individuals. They now said the intrinsic rate of growth is 0.34. You understand? 0.34. They now say you should look for it in 5 years. So time equals to 5 years, right? Then r equals to 0.34. It is not difficult. What you're just going to do is nt equals to n naught exponential rt. That is equals to what? That's equals to nt. What's our nt? Our nt is that is our n naught is 234 exponential 0.34 multiplied by 5, right? Now, if you press our calculator, if you press 0.34 multiplied by 5, you will have 1.7. Then exponential 1.7, you have 4.62. So that is 234 multiplied by 4.62, I guess. Yeah, 4.62. And if you multiply it, you are going to be having what? Multiply by 234. We have 1081. That is the total number that it will be in 5 years. You understand? Or multiply by 5. I think I made a mistake. I said multiply by, yeah, 0.34, right? 0.34 multiplied by 5. Then 234. 234, right? Multiply by exponential 0.34 times 5. I have 1280, 1280.9, 1280.9. You understand? That is 1280.9. I think exponential 1.7, exponential 1.7 is supposed to be, exponential 1.7 is supposed to be 5.47. I made a mistake. 5.47. So that will be 1280.9 individuals, which is approximately 1281 individuals in what? In 5 years. You understand? So that is how the exponential curve works. But it cannot happen in real life. It is not possible for something like that to happen in real life. There is no real life situation where you will find unlimited resources. It is not possible. Therefore, we now incorporate the next one, which is the what? Which is the logistic growth model. So exponential growth model is only possible where there is infinite natural resources, and it is not like that in real world. So Charles Darwin recognized this fact in his description of struggle for existence, which state that individual will compete. There is no possibility. There must be competition for resources. There must be competition, and this competition is because the resources is what? The resources are limited. You understand? There are limited resources. There will be competition, and where there is competition means there is going to be what? There is going to be the successful ones, and the successful one is going to pass the trait from the first generation to the another. And to model this reality of limited resources, population ecologists get into what we refer to as what we refer to as logistic growth model. Now, this logistic growth model is capable of happening in real world. What does logistic growth model state? You see, because there is limited resources in real world, exponential growth cannot continue indefinitely. You understand? So it may occur in an environment where there are few individuals and there are plentiful resources. But when the individuals get large enough, resource will deplete, there will be slowing down of growth rates. Eventually, the growth rate will plateau or level off. You understand? Now, in real world, eh, when a population continues growing, when a population continues growing, it will reach a particular point where it will stop growing and it will start moving like this. You understand? Where it will stop growing and start moving like this because the resources is limited. You understand? The environment cannot take more than that population. You see the point at which the environment cannot take more than, like, the maximum number, the maximum population size that an environment can support is what we refer to as carrying capacity, and it's represented with K. Like, that is the last capacity that a particular environment can support. Anything more than that, an environment cannot support it. Now, in this carrying capacity, it is not like it is a particular point at which population cannot grow again. Either the population goes straight, or it's what? It's either it goes straight or it comes down. You understand? Or it declines. You see, the first one, which is exponential growth, is what we refer to as J-shaped curve. J-shaped. It is J-shaped. You understand? You now see this logistic is S-shaped. This one, it is S-shaped. You understand? Or we call it sigmoid shaped. You understand? Now, the formula for calculating this particular exponential growth is given as what? Is given as dn over dt equals to Rn. Let me cancel this out. Equals to Rn, right, into bracket k minus n over n, which is what? What our k is what? Our k is carrying capacity. So carrying capacity is that point at which the environment cannot take more than that population. You understand? Let's take for an example. Every admission, University of Ilorin accepts only 10,000 students, like 10,000 freshers. You see that particular 10,000, that is the carrying capacity of 100 level of University of Ilorin. Anything more than 10,000, University of Ilorin is not going to accept it again. That is basically what that's the maximum population that 100 level porter can support. You understand? That is basically what they are trying to say in that particular case. So now, in this, we have the exponential phase, that's the low population abundant resource. We have the deceleration phase and we have the equilibrium phase. You understand? In logistic model, we have the exponential phase, we have the deceleration phase, and we have the equilibrium phase. I'm still going to talk about what they mean by all of this. All this logistic growth, I'm still going to talk about what they meant by that. I just want to check the next thing. Now, look at this particular question. Look at this question. They said that the shelf life, the wild refugees along the coast North Carolina home 92 American oyster catcher birds, right? Oyster catcher birds. So we have 92 oyster catcher birds, right? They now said the carrying capacity is 200. We have the carrying capacity here to be 200. Look at this. Open to build is 200, right? They now give the birth rate. Now look at it. They said that scientists are hoping to build up the population 200. Since they know that refuge can support this many individuals. After doing some research, you learn that for every 50 birds, 30 birds are born annually and 22 birds die annually. You understand? What is the population of 92 birds at the refugee expected like that's expected next year? You understand? Now, what is going to happen here is that we have our number of individuals to be 92. We have our carrying capacity to be 200. We have our birth rate to be equals to 30 births. 30 out of 50 is being given birth to. So 30 over 50, that is 0.60. Then death is what? Is 22 over 50. That is 0.44. Which means our intrinsic rate, remember intrinsic rate is B minus D. And if you subtract 0.60 from 0.44, you are going to get 0.16. So it is not difficult again. Just input it. You understand? Which means our dn upon dt equals to what? Equals to 0.16, which is rate, multiplied by what? Multiplied by 92, which is n, multiplied by 200 minus 92, which is k minus n, divided by n, which is 200. You understand? And that is equals to what? That is going to give us 14.72 multiplied by 0.54. And that is going to give us what? That is going to be giving us, which means our dn upon dt, which means increase in with respect to time, is going to give us 7.95, which is approximately 8. You understand? Now, which means the estimate in next year is now going to be how many of them are there in this year? That is 92. So it's going to be 92 plus the 8 that we got here. And that's going to give us what? That's going to give us 100 individual births in next year. You understand? That is the number of births that we're going to be having next year. You understand? So that is basically how to solve questions under the logistic growth model. You understand? Now, let me now explain the concept of logistic growth model in an actual sense. How can we understand the logistic growth model in an actual sense? Now, let us take for an example. we have an environment. This is an environment, population, time. We have an environment. In this environment, we have sugar. We pour sugar down. You understand? Now, what is going to happen is that an ant will come. You understand? It will come. It will come and taste the sugar. Or two ants can come to taste the sugar. You understand? Or three ants can come to taste the sugar at the same time. Are you getting me now? Now, when they taste the sugar, there are a lot of sugar here. What they are going to do is that they are going to signal the others. They are going to signal the others to come using a particular chemical that they refer to as pheromones. The pheromone is what they use to communicate with others. They come. Now, when they come, you see that it is only three that started the population. But very soon, three will become six. Six can become like 10. Like 10 of them will start coming. Before you know it, you have 100. You have 1,000 ants in a particular area. Now, at a point, the sugar will what? The sugar will decline because they would have finished the sugar that is there. You understand? They would have finished it. It will decline. Which means at that point, the environment does not support their survival again. They will start, all of them will start competing for what? They will start competing for the sugar. Some of them will die, some of them will live. Which means what happened to the environment? What happened to the population? The population falls. So if you put another sugar there, what happened to the population? Those ones that have left, they will come back, even bring more people. When the carrying capacity is reached, you see that point at which it cannot survive, like they cannot adapt anymore. Some of them are dying and some of them are living. That is what we refer to as carrying capacity. You understand? So look at it. Let us say that it is like this. So let us say that it is like this. Let us say that this is ants, three ants that are here. You understand? These are three ants. They taste it for like 3 minutes. You understand? So this is 3 minutes. They taste it for like 3 minutes. Then call pheromones to signal the others. They start coming. Three become what? Three become six. You understand? Six become 100. 100 become 1,000. You understand? Now it will reach a point at that 1,000. What will happen? The population will slow down. It will slow down at that particular point. Then it will reach a particular point where the population will be stable. It will not accept more than that. You understand? Then what happens to it? It will now decline. You understand? Some of them are dying and some of them are moving out. When you now put another sugar, they come back up. When they finish it, they go down. They come back up, they go down. You understand? You see this particular point? This point at which they are oscillating, this point that they cannot go more than this point. That is what we refer to as what? That is what we refer to as carrying capacity. This particular point that is here, that is what we refer to as carrying capacity. They cannot go more than this. So you are going to represent this as what? As K. Do you understand? So this is the population growth with respect to time. Now, if you look at it very well, what are the things that we have here? We have the what? We have the lag phase, right? We have the exponential phase, the phase that look like exponential growth, like this J shape that I draw before, right? Can you see it look like J? Exponential phase. You will see the equilibrium phase. That is the phase that is flat, that they are not growing anymore. This particular phase that is flat. Then you see that deceleration phase, the one that they are now going down. So this is exponential phase. This is deceleration phase, which is stationary phase, and this is what? This is stationary phase or equilibrium phase. You understand? So let me say stationary phase or equilibrium phase, and this is what? This is deceleration phase or declination. They call it declination. Now see this particular point that is here, that is the carrying capacity. And that is basically what the concept of population growth is. So if you use logistic model, carrying capacity is known. If you use exponential group model, carrying capacity is unknown. You understand? And this is the first part of the population growth model that we are going to be talking about. In the next video, we are going to talk about what are the factors that regulate population growth? What are those factors that are involved in the regulation of population growth? The next video. Thank you and God bless you.